niece's bedroom. It's been a curious few weeks, so please excuse the not exactly production quality streams, but we make do. So today, so on in the Alt Deep community on Monday, we have a reading group on this simulation-based test of identifiability for Bayesian causal inference by Sam Woody, David Denson, and Vikash Manshinka. I'm excited to read the paper. Sam will be in the reading group, so I'm just gonna, listen. Live streaming paper readings isn't the funnest thing in the world, but honestly, uh, reading papers isn't the funnest thing in the world. so maybe if we can share the burden with one another, it makes it a little bit easier. But I can't see the comment view. Let's see here. I want to be able to see if people comment. There we go. Okay, so can I get that front and center? Okay, so this will work. So this paper introduces a procedure for testing the identifiability of Bayesian models. I want some music. Sorry, I'm going to need to listen to something. So Twitch has and YouTube, streaming to both of these places, has some DRM sensors that'll kind of, you try and play music. Once I tried to play some Spotify music and it stopped me. Let's do focus. This is brain.m. They do like like this. It's supposed to help you focus. I'm not even sure if it's coming through. Is it coming through? Sounds like it. Turn the volume down a little bit. Okay. Paper introduces a procedure for. So I'm hoping that they don't pick up on some DRM and totally shut down all the audio in this stream, because that would defeat the purpose. But let's forge ahead. This paper introduces a procedure for testing the identifiability of Bayesian models for causal inference. Although the due calculus is sound and complete given a causal graph, many practical assumptions cannot be expressed in terms of the graph structure alone, such as the assumptions required about instrumental variable designs, regression, discontinuity designs within. Hold on, I'm gonna see here. Sorry, 1 second. I have some notifications that are. Let's close some apps here. Overburden the. Okay. Within subjects' designs, we present a simulation-based identifiability, a fully automated identification test based on a particle optimization scheme with simulated observations. This approach expresses causal assumptions as priors over functions in a structural causal model. Priors over functions in a structural causal model, including flexible priors using Gaussian processes. We proved that SBI is asymptotically sound and complete and produces practical finite sample bounds. We also show empirically that SBI agrees with known results in graph-based identification, as well as widely held intuitions for designs in which graph-based methods are inconclusive. So, kind of zooming out, we know that if we have the graph, we can identify causal queries using the due calculus. So, I'm sorry, if you're kind of seeing this, you're new to causal inference, we have this idea of representing a causal model with a directed graph. And there's this theory called the due calculus. It's basically a set of 3 rules that you use to prove things. You use to prove, kind of like how, back in high school geometry, you would use rules to prove that you know, the angle of to prove that an angle of a corner in a triangle had a certain amount of degrees or something like that, right? So here, the thing that we do in causal inference is to say, hey, I have some observational data. Well, most of the time, what we do is we have some observational data, and we say that we want to use this observational data to identify something that's that's causal in nature. We know that that correlation that you observe in observational data doesn't imply causality. The rules of the do calculus allow you to prove when you can take some statistical observations you make on observational data and conclude and determine that you can infer causality from that data. And then once you've inferred causality, you then have to go do some statistics to actually estimate the causal query. So, but there are some causal queries that can be identified, but in order to, with information above and beyond what's inside the graph, right? So instrumental variables is one example. And so what they're doing here is they're going to take a Bayesian approach. They're going to define something called a structural causal model, which is if you're familiar with structural equation models, it's like that. You have a graph, and on top of the graph, you have some functions defined that kind of map each parent to the child, and those functions, they're taking the approach of putting priors on those functions. So looks like they're going to use Gaussian processes, possibly something else. So it sounds very interesting. I'm excited about reading. All right, so the way I tend to read a paper is I'll read the introduction, then I'll basically look at the section titles and the images, and then read the conclusion, because then you get a kind of skeleton of the paper, and then you can flesh it out if you need to. Maybe after you read all that, you get all that there is to it. There's a lot of reviewers who review papers who just do that. So if you're a good paper writer, you understand that reviewers are lazy and try to make the information easy to scoop up. So let's see if we can't do that. Given a causal graph, to do calculus is a sound and complete procedure for nonparametric identification. However, graph structure alone tells us an incomplete story of causal knowledge. Instrumental variable designs require monotonicity or linearity. Within subjects, designs require that latent confounders are shared across units. And regression discontinuity designs violate positivity assumptions that are implicit in the do calculus. The do calculus is inconclusive for these designs because it ignores the necessary restrictions on structural functions. Great. So just making a case that there's a lot of stuff that we can do if we go beyond do calculus, or in other words, we don't want to rely on the do calculus alone. And this is actually a really strong argument for combining kind of Bayesian methods and probabilistic programming. I mean, I know Vikash Manchika is definitely a probabilistic programming person. Sam Whitty and David Judson also fall into that community. Although David Judson does a lot of things, and so like this idea of kind of building probabilistic models and putting priors over things that you're uncertain about. There's a lot. Being able to use that as a way of getting at the core problem of identifying causal queries, and even more saying that one of the things that some of the folks in the pure do calculus world do is like when they can't identify things, they like to construct bounds and try to figure out, okay, well, can we bound something within something, and there's a very natural Bayesian approach to doing that, which is to say, like, because we don't need to bound what we can determine, what we don't determine. If we're being Bayesian, we can just work with priors and posteriors, and even within said bounds, kind of weight some things more than others based on prior knowledge. So I think this is, I've been pretty excited about this line of work. Historically, practitioners have circumvented the limitations to do calculus by either avoiding novel causal designs altogether or constructing cumbersome proofs from first principles. This paper proposes an alternative. Express causal assumptions as priors over structural causal models, implicitly inducing a joint distribution over observed and counterfactual random variables, and 2, search for models that are likelihood equivalent, but that produce different effect estimates. That's interesting. So likelihood equivalence means that the models will all provide the same likelihood. They all explain the data. They all provide equally likely explanations of the data. And but these different explanations would yield different answers to causal queries. And so that seems to be what they're trying to get towards. So we introduce the simulation-based identifiability, a flexible and automated identification technique that is compatible with any prior over structural causal models that 1, can be used to sample data, and 2, introduces a differentiable likelihood function, or induces rather. SBI translate the problem of causal identification to optimization procedure that seeks to maximize the likelihood of 2 candidate structural causal models while maximizing the distance between their causal effect estimates. If the optimal solution to this procedure is 2 models that agree on effect estimates, then the causal effect is identifiable. Let's see that again. Maximize the data likelihood of 2 candidate. All right, so we get 2 structures. Great, and okay, but we're not going to parameterize those structures. We're just going to do what? We're just going to. I wonder how how do you get the likelihood of a structure unless you fit parameters to it? SBI translates the problem of causal identification to an optimization procedure that seeks to maximize the data likelihood of 2 candidate structural causal models while maximizing the distance between their causal effect estimates. Maximize the likelihood of 2 candidate models. Maximize the distance between their causal effect estimates. The optimal solution to this procedure is 2 models that agree on effect estimates. Then the causal effect is identifiable. That's interesting. So you're trying to so it's an optimization procedure that is trying to somehow get the models to disagree on a causal effect estimate. And then if they fail to disagree, then, okay, so let me think back to equivalence classes. So we got an equivalence class of causal graphs. All of them will have the same data likelihood if we were to parameterize them using the same parameterization, say if we use maximum likelihood estimation. So so within that space of equivalence class, I could pick 2 of them, and then let's say that class for some reason only had 2 members, and were to and that class has the maximum possible likelihood. And then I estimate causal effects on both of them. But how do I maximize data likelihood of 2 by maximizing the distance between their causal effect estimates? So I guess we're going to have to figure out what this distance metric is. If the optimal solution to this procedure is 2 models that agree, then causal effect is identifiable, which I suppose would require a proof. Figure 1 provides intuition for how SBI uses gradient-based optimization to determine causal identifiability. Let's jump down to figure 1. Figure 1, come on down. Okay. Alrighty. Causal effect. Got some gradient pictures here. Guess that's where we want to go. Causal effects on the x, nuisance parameter on the y. And we're looking at certain horizons at this. All right, not making much sense of that. Here is a concave something or other. Let's see here. Got treatment. Got the effects. Got a confounded. Got some structural causal. Got some functional equations here from in the structural causal model. And here we have confounding. We've got a mediator here. X here in the middle between the treatment and the outcome. Simulation. Okay, Simulation-based identification discovers likelihood equivalent causal model. Simulation-based identifiability maximizes the data likelihood and the distance between causal effect estimates induced by two structural causal models. When the causal effects are not identifiable, a simulation-based identification simulation-based identifiability discovers maximum likelihood models, blue and red, that estimate different causal effects. Okay, so we're trying to push them apart in this optimization, and if we succeed, then causal effects are not identifiable. When they are identifiable, the likelihood dominates, and the two models converge to the same causal effect. That's interesting. It's also weird because these models don't look equivalent to me. They don't look. I guess likelihood equivalence doesn't mean the same as. All right, so I guess before I was talking about equivalence class. I said likelihood equivalent. Okay. I guess I'm trying to figure out what makes these models equivalent. Like, I don't see how these two models here would be equivalent in likelihood, if only because there is a different set of, well, it depends on, I guess, what you observe. But I'm observing you observe here, here you observe t and y, here you observe t, x, and y, so you have different joint distributions. So joint likelihoods, by definition, are not even the same dimensionality, so I'm not very equivalent. The likelihood dominates and the two models converge to the same causal effect. Simulation-based identifiability is fully automated for any prior over structural causal models with differentiable likelihood and causal effect, covering quasi-experimental designs that previously required random custom proofs, including semi-parametric versions. What happened? Okay. Simulation-based identifiability discovers maximum likelihood models, blue and red, and estimate different causal effects. And when are identifiable, likelihood dominates, they converge. Simulation-based identifiability is fully automated for any prior over structural causal models with a differentiable likelihood and causal effect. So you just have so all you need to start as a prior and a causal effect. But it's interesting that they had a video or something covering quasi-experimental designs that previously required custom proofs, including semi-parametric versions using Gaussian process priors. Section 4, we proved that SPI is asymptotically sound and complete. Right, so they got proofs. We, assuming certain strong regularity conditions are met by the structural causal model, provide pack-like bounds in the case of finite samples, and present an algorithm that can be implemented in any differentiable generative probabilistic programming language. In section 5, we showed that SPI is broadly applicable by presenting Bayesian variants of a suite of well-studied quasi-experimental designs, such as regression discontinuity, instrumental variables, and within subjects designs. We also present their semi-parametric extensions using Gaussian processes, further demonstrating SPI's flexibility. We go on to show empirically that SPI correctly determines the identifiability of well-studied parametric causal graphs and quasi-experimental designs, including those not by the do calculus. Finally, we use SPI to extract quantitative insight about several Gaussian quasi-experimental designs, which is pretty exciting. Interesting. Okay. Let's go over the section. So we saw this already. We expect convergence here if we get some kind of causal effect, and causal designs covered. So here's what we're going to actually be able to solve with this approach. Unconfounded, confounded, backdoor, front door, instrumental variable within subjects, regression discontinuity. So unconfounded latent variables influence treatment or outcome. Confounded, a latent confounder U influences both T and Y. An observed confounder X influences T and Y. That's backdoor. So unconfounded is we have latent variables on T and on Y, but not both. Front door U influences T and Y, but does not influence the observed mediator X. Instrumental variables U influences T and Y. An observed instrument influences T, does not influence X except through T, is not influenced by U. Within subjects, each instance of U influences multiple within subjects, each instance of U influences multiple instances of T and Y. Regression discontinuity. An observed confounder X influences T and Y and T depends on X being above or below a certain a known threshold. What is that? So each instance of U influences multiple instances of T and Y. Right. Okay. And then regression discontinuity. An observed confounder X influences T and Y. T depends on X being above or below. Right, so T depends on X being above or below a known threshold. Okay. That's popular in economics, isn't it? So we're going to talk about priors. Right now I'm just giving a paper a scan. Got some theorems, identifiability. Let's look at the, all right. Let's look at the first algorithm here. We got some prior on, I guess, functions on some exogenous variables u. Not sure what epsilon is. Causal estimand and interventions. So we got a query. Whatever those are, I guess they mean interventions somehow. Got some hyperparameters. We simulate f and u. Okay, and then we loop simulating some variables. That must be like the number of variables there. We're maximizing some kind of likelihood. This must be, okay, sorry, this must be 2. So where this indexing came from. Where did F1 and F2 come from? Yeah, I'm actually really comfortable reading papers and not knowing what the heck is going on. That's they're meant to be kind of information dense and to convince knowledgeable people, and I guess I am knowledgeable about this stuff. Would help if I read it, but right now I'm scanning. So we get 2. I just want to see what we're trying to get at here. We're maximizing some differentiable likelihood using gradient descent. I guess we're getting 2 of something, 2 models. We're perhaps now making sure we're F. Oof. Okay, looks like we're trying to get some kind of difference between 2 things, as we talked about before. Do some kind of right, this looks like a significance test to make sure that it's the difference between these 2 things are statistically significant, and if they are not, with some threshold, maybe alpha, so 0.05 or something like that, threshold acceptance probability. Then we say that it's identifiable, else it's not identifiable. Interesting. So it's identifiability. So do calculus gives you identifiability based just on the graph before you see any data. Since this algorithm incorporates likelihood, and we're reasoning using, it's an empirical test of likelihood. Sorry, an empirical test of causal identifiability. This would require, assuming the proofs that are coming are going to be pretty hefty. It's going to be, it'll be stats proofs, though. He's got to show that something converges to something in the asymptote. I got some theorems, great. Got some hyperparameter selections. Kind of rules of thumb, I imagine. Here's another figure. All right, figure 2. Simulation-based identifiability is correct for flexible Gaussian process causal models. High values of delta Q hat for the confounded Gaussian process model indicate that the treatment variable is not identifiable. Without confounding, however, the 2 optimized particles converged. Interesting. I wonder why these, when you don't have it was curious to me that when you don't have identifiability, you get whatever these bounds are tend to be. So this is the difference between the 2 models. So you can get a little bit of a difference here. And This is a bit surprising to me that this difference can have so much variation relative to. Wait, what? Isn't when the two models are not identifiable we expect more difference? But this is more difference. We're going high, this is low. Okay, we have more variation. Junior's coding says hello, sir. Hello, Junior's coding. I am not too bad. What I'm doing right now is I'm reading this paper on simulation-based analysis and what is it? A simulation-based test of identifiability for Bayesian causal inference. Right now, I'm just kind of scanning over the paper. It looks like we're pretty dense on the math, which you would have to be for something like this. You'd have to prove that we're getting some kind of conversion. Let's look at the math, see if I can just scan it and make heads or tails of what's going on. All right, some kind of breakdown of the log likelihood. The above expression shows directly from the fact that what's so important here? Why are we showing stuff here? We've got a log normal plus another log normal, and then we break down. Okay, we have all u k. Where's k? Okay, not sure where k star is, but looks like we're breaking down some likelihoods. Looking at some derivative of this difference, q. What are we trying to accomplish here? An example, confounded Gaussian process regression. All right, and even more math. Let's look at figure 3. Simulation-based identifiability agrees with known parametric results. SPI correctly determines that of the causal designs we cover, the above treatment effect is identifiable for all except the confounded regression model. So that was confounded regression, instrumental variable. So we're just showing that as we do gradient-based learning, that this loss function, this delta Q, is difference between the two approaches to estimating a causal effect is decreasing. Okay, this is empirical evidence. Table 2, simulation-based identifiability accurately determines identifiability for diverse causal designs. What are we looking at here? Back door, front door, very well. Okay, so we have some ground truth for these things that are identifiable, things that are not. We're looking at some confidence intervals for the difference. SPI outperforms the baseline. Oh, I see, we're comparing to some kind of baseline approach, resulting in near perfect identification results for the average treatment effect. Values are shown in bold if SPI or the baseline correctly determine identifiability out using a threshold of 5% on the true effect. Okay. Okay. SPI provides novel insight that the Gaussian process quasi-experimental design agree with nonparametric identification result. Nonparametric. Okay, I get that. Not much to comment on there. Causal graphical models, linear quasi-experiment designs. Simulation-based identifiability agrees with widely held intuition for regression discontinuity designs. What is that widely held intuition? I'm searching myself for the widely held intuition. I don't see it. Conditional average treatment effects are only non-parametrically identifiable infinitesimally. You know what? I want to go and watch a quick video on regression discontinuity designs just to refresh myself here. I'll do that. What? Oh, that's what it says. In stats, econ, political science, epidemiology, pre-test, post-test design that supposedly elicits the causal effects of interventions by assigning a cutoff or threshold above or below which an intervention is assigned. Okay, that's different from how I learned it. I learned something else. By comparing observations lying closely on either side of the threshold, it's possible to estimate average treatment effect in environments in which randomization is infeasible. Yeah, okay, that sounds familiar. However, it remains impossible to make true causal inference with this method alone, and it does not automatically reject. If you can't make true causal inference, it does not automatically reject causal effects by any potential confounding variable. And then some, and it looks like they're popular and they've been comparing them. Examples, the intuition behind regression discontinuity designs is well illustrated using the evaluation of merit-based scholarships. The main problem with estimating the causal effect of such an intervention, so that's a scholarship, so the scholarship is I give you an intervention, the outcome is, I guess, is you do well in school or you go to school. The homogeneity of performance of the assignment of treatment. Homogeneity of performance to the assignment of treatment. Wow, it's like, oh man, these assignments of treatment. Wait, no. Oh no, these assignments of treatment are. Wait, I'm trying to understand this one. This is the phrase. All right. Main problem is the homogeny of performance to the assignment of treatment. Homogeny of performance to this assignment of treatment. Okay. Since high-performing students are more likely to be awarded the merit scholarship and continue performing well at the same time, comparing the outcomes of awardees and non-recipients would lead to an upward bias of the estimate. So this feels like effective treatment on the treated. Like the people who get, you want to understand the effect of scholarships on people, but the people who get the scholarships were already doing well. Had they not gotten the scholarships, they probably still done all right. And so what you want is So there's confounding basically by the people who are getting the scholarship are, one second. The people who are getting the scholarship are, well, you're more likely to get the scholarship if you're already good. Your outcome the outcome the outcome is also based on whether or not you're already talented and merititious. So what we're going to do about that? So yeah, we get an upward bias. Right. So even if the scholarship did not improve grades at all, the awardees would have performed better than non-recipients simply because scholarships were given to students who were performing well ex ante. Despite the absence of an experimental design, an RDD can exploit exogenous characteristics of the intervention to elicit causal effects. If all students' grades are above the given grade, for example, 80%, are given the scholarship, it is possible to elicit the local treatment effect by comparing students around the 80% cutoff. Right, this is how I've learned about regression discontinuity. Is you look close to that cutoff. A student here scoring 79% is likely to be very similar to a student scoring 81%. Given the predefined threshold of 80%, however, one student will receive a scholarship and one will not. Comparing the outcome of the awardee, so you basically so I think what you want to do is kind of compare that 81%er to that 79%er. One second here. The most common approaches to estimation using an RDT are nonparametric and parametric. Let's see, most common nonparametric method used in the RDT context is local linear regression. All right, so we got alpha plus delta D plus beta 1 x minus C plus beta 2 D x minus C plus A, where C is the treatment cutoff. All right, so we're kind of centralizing on the cutoff. D is a binary variable equal to 1 if x is greater than the cutoff. H is the bandwidth of the data used. Wasn't even H in there. Let me see H. Letting H be the bandwidth of the data used, we have C minus H is less than X is less than C plus H difference. So that's okay. So that's like I guess how close to the cutoff we want to be, maybe. Different slopes and intercepts fit data on either side of this cutoff. Typically either a rectangular kernel or a triangular kernel are used. Research favors the triangular kernel. The major benefit of nonparametric methods in an RDD is to provide estimates on data closer to the cutoff, which is intuitively appealing. This reduces some bias that could result from using data further away from the cutoff to estimate the discontinuity at the cutoff. More formally, local linear regressions are preferred because they have better bias properties and have better convergence. However, they use both types of estimation. If feasible, is a useful way to argue that the estimated results do not heavily rely on which approach is taken. So here's a parametric explanation. So we got, all right, so we got cutoff squared. So we're using the cutoff as a kind of regressor, and xi is 1, c is greater than, what's c bar now? C bar is the treatment cutoff, okay. So now what's c now? C is the treatment cutoff. Okay, that's non-parametric. So ci is, okay, not sure what ci is. It's not defined here. Okay, I think that gives me at least a gut understanding of what we're doing here. Simulation-based identifiability agrees with the widely held intuition for regression discontinuity designs. K's are only non-parametrically identifiable and infinitesimally close to the discontinuity. Here, x, we're interested in x on the effect of y. While average treatment effects for linear models are well known to be identifiable, the identifiability of Gaussian process versions are previously unknown. SPI provides novel and intuitive identification results that effects become less identifiable as we condition on covariates further from the discontinuity. Okay, so that's the intuition. Novel and intuitive identification results that effects become less definable. So B. All right, so as we get we're going, so this must be different from the discontinuity, and we see the identifiability going down. All right, let's jump right into the discussion. So in addition to being more flexible than prior automated approaches, SPI can be used as a kind of sensitivity analysis, bounding the range of causal effects that are likelihood equivalent. Our regression discontinuity design experiments in Figure 4c emphasize this capability. Bounding the range of causal effects that are likelihood equivalent. Okay. Our regression discontinuity design experiments in 4c emphasize this capability, showing that irreducible uncertainty in effect estimates increases as we condition on covariates further from the discontinuity. SPI builds on a long history of optimization-focused machine learning research, reducing identifiability to optimization in this way provides a path towards reasoning about causal designs at previously unobtainable scales, which is an exciting area of future work. So that's an interesting way to articulate the contribution. Like identifiability is typically a yes or no thing, right? Like either a causal query is identified given the assumptions or it's not. And the idea is that once we kind of go into the parametric realm, so going beyond the structure and reasoning about a due calculus, we're saying like identifiability here is continuous, right? It's not a yes no, but it's like at least we can kind of soften it a little bit and think of it as something that we can try to reason as, we can think of it as something that's on the scale, and then we can use optimization to to try to suss it out. So we do this a lot in machine learning with gradient techniques, is to say, here's some kind of hard, discrete problem, and we're going to soften it so that we can search it using gradient descent. I like it. I guess part of me, the inner causal inference fanatic, extremist, balks at the idea that you can think of identifiability is a true or false thing, but we're talking about a host of parametric techniques where we're talking about parametric identifiability, and that I guess I need to mull on this a little bit. Kind of what does it mean to have a soft identifiability based on parametric assumptions? Well, no, it makes sense, because again, if we're being Bayesian about structure to begin with, then we've already softened the hard binary problem to one that is we're being Bayesian about the structural causal modeling functions. Then this makes a lot of sense. I don't know if I'm making sense. I might be too in the weeds or too tired to make sense. I guess what I want to say is identifiability is certainly a yes or no question. However, if we're being Boolean about the assumptions that go into if we're being Bayesian about the assumptions that go into answering that yes or no question, then the yes or no question becomes soft, becomes a continuum, and we're trying to figure out where we land on that continuum. In this paper, we presented a simulation-based identifiability, an automated approach for causal identification. In section 4, we proved that SBI is sound and complete in the limit of infinite samples and compute, and provided practical finite sample bounds. In section 5, we demonstrated that SBI correctly determines identifiability empirically with 7 well-studied causal designs, 3 of which are out of scope for the do calculus. We hope that SBI can embolden practitioners and researchers to rapidly iterate and explore novel designs for causal inference. Awesome. Well, I enjoyed that. Obviously, we didn't get to go dive into the meat of the paper. We never have time to do that. I hope that is useful for people who are kind of looking at this for the first time. I will continue to read this offline. But we get at this point now, we have an understanding of what the paper is attempting to do and what the contributions are and why we think those contributions might be important. So that's a good way to wrap up. If you're interested, if you're in the Alt-Deep community and you want to join the discussion group on this, it'll be a good one, because it'll be, this guy is in the group, he's in the community. So is David Jensen, actually. I don't know if he'll join though, but he'll be able to talk about his own paper. We can ask questions, but you should read the paper if you join. It's on Mondays at 3 p.m. Eastern Time, United States. That's so 3 p.m. New York time. And okay, hopefully I'll see you there. If you're not a member of the community, I'll be sending out information soon for how you can apply to join. But if you want to join this reading group, just ping me somewhere and I'll make sure that you get a Zoom link.